Today, we're diving into one of the absolute cornerstones of quantum computing, the Quantum Fourier Transform. You can think of it as a secret decoder ring, a tool that lets us find hidden patterns and secret rhythms that are encoded in the very fabric of quantum information. It lets us uncover secrets that classical computers, well, they could never even dream of finding.
Just think about listening to music. Your ears don't just hear a jumble of noise, right? They can somehow pick out the melody from the bass line, the drums from the guitar. The Fourier transform is basically the mathematical version of that. It can take any complex signal, whether it's a sound wave, a stock market trend, or even a quantum state, and it breaks it down into all the simple, pure frequencies that it's made of. All right, so here's our game plan. First, we'll get a handle on the classical idea of finding these rhythms. Then we'll jump into the quantum world to see its supercharged upgrade, the QFT. After that, we'll talk about its mind-blowing speed, see its most famous trick with Shor's algorithm, and then wrap up with why this one tool really changes everything. Okay, so before we can really appreciate the quantum version, we gotta get familiar with its classical parent, the discrete Fourier transform, or the DFT for short. So what you're seeing here is the DFT in action. On the left, you've got this messy, complicated-looking signal as it changes over time. The DFT acts like a prism for data. It takes that signal and separates it out into its pure, simple frequencies, which you see on the right. This is a huge shift in perspective. We stop asking when something happened and start asking how often it repeats. So that's the textbook definition, but really the DFT is a workhorse. It's in everything from your phone's microphone to NASA's satellites. Its entire job is to find those hidden repeating patterns, those secret rhythms in any stream of data. Okay, time to head into the quantum world. This is where this powerful idea gets a truly massive upgrade. Seriously, this is where things get really, really cool. And here is the quantum leap. The Quantum Fourier Transform does the same job as the classical one, but its approach is totally different. Instead of analyzing data points one by one, it operates on a quantum state that is holding all possible values in superposition at the same time. It's performing the Fourier transform on the probability amplitudes of the state, which you can kind of think of as the importance of each value. It's like it's listening to every possible rhythm all at once. This really gets to the heart of it. You can think of the QFT as just rotating your point of view. It doesn't actually change the information in the quantum state. It just lets you look at it in a completely new way. It shifts the state from the standard zeros and ones basis into this new frequency basis. And that rotation suddenly makes information that was totally hidden in the quantum phases pop right out into the open.
Now, you might look at this circuit and think it looks a little intimidating. But here's the beautiful part. This incredibly powerful transformation can be built from a really simple and elegant sequence of just a couple of basic quantum gates. And that efficiency isn't just nice to look at, it's the entire key to its power. And yeah, that efficiency, that's the whole game. So why is building this one circuit such a massive breakthrough? Well, the answer is the absolutely mind-bending speedup it gives us over any classical computer that could ever exist.
Let's try to put this in perspective, because the numbers get crazy fast. To analyze, say, 1 million data points, a classical computer needs millions of steps. A quantum computer, it can represent those million possibilities with just 20 qubits. And to do the same transform, it takes just a few hundred steps. The difference isn't just big, it's exponential. As the problems get bigger, the quantum advantage just becomes astronomical.
I just want to pause on this for a second. We have to be super clear here. This isn't just a bit faster. It's not like going from a car to a plane. It's like going from walking to teleportation. For a system with just a few hundred qubits, a quantum computer could do a Fourier transform that would literally take the biggest supercomputer on Earth longer than the age of the universe to finish. Okay, so we have this unbelievably powerful tool. So what do we do with it? Let's look at its most famous or maybe infamous application. Using the QFT to break the very encryption that protects most of our digital world. So much of our digital security, from your online banking to secure government communications, it all relies on a simple mathematical truth. Multiplying two huge prime numbers together is easy. But starting with that big result and trying to find the original two primes, that is an impossibly difficult task for any classical computer. That's the factoring problem. Shor's algorithm is it's pure genius. It cleverly turns the hard problem of factoring into a much easier problem, finding a hidden rhythm. Here's how it works. It encodes a special function into a quantum state. And the rhythm, or the period of this function, is mathematically tied to the factors we're looking for. Then the QFT comes in, acting like that perfect ear, and it just listens to the quantum state and pinpoints that hidden period. Once you have the period, a little bit of classical math is all it takes to find the factors. It's incredible.
And this is what's happening under the hood. You start with this quantum state that has a periodic pattern hidden in its amplitudes. The QFT transforms it. Now, the new state isn't periodic anymore. Instead, almost all of its probability gets concentrated, or peaked, at frequencies that are directly related to that original hidden period. So when you measure the state, you have a super high chance of getting the exact piece of information you need.
So let's pull all this together. What's the really crucial point you should walk away with from all of this?
Here are the big ones. The QFT is the quantum cousin of the classical Fourier transform. Its superpower is finding hidden, repeating patterns. It does this with an exponential speedup, which is the key that unlocks world-changing algorithms like Shor's, the one that can threaten modern cryptography. But, and this is a really important but, there's a twist. A classical Fourier transform gives you the whole beautiful spectrum of all the frequencies. When you measure a quantum state after the QFT, the whole superposition collapses and you get just one single answer out of all the possibilities. This is the real genius of algorithms like Shor's. They're carefully designed so that when you make that one single measurement, the answer you get back is, with very high probability, the exact one you were looking for.
So let's end with this thought. We've seen the QFT as this incredible tool for breaking codes by finding mathematical rhythms. But at its heart, it's a fundamental tool for understanding patterns, period. So the big question is, what other hidden rhythms in chemistry, in drug discovery, in material science, or maybe even in the laws of physics itself, are just out there waiting for a quantum ear powerful enough to finally hear them?